So, what did we discuss in the last session?
When we started statistics. Hello?
Okay, okay. Yeah. So, in today's session, we will continue with the statistics part. Yeah, now, in descriptive statistics, we have seen three major categories, right? If you remember,
Two were
descriptive,
fringe and quartile.
yeah, so measure of central tendency, then measure of
Shape.
dispersion,
Measure of
and third is measure of.
shape.
Your voice is very less. Measure of
Shape.
shape. Right. Measure of central tendency we have discussed mean, median, and mode, right? In measure of dispersion we have skewness and kurtosis. In measure of shape, what do we have is
सर शिफ्ट हुए क्यों मेजर ऑफ डिस्पर्शन में रेंज क्वार्टाइल है मेजर ऑफ शेप में क्वार्टाइल होता है
sorry. Measure of shape is kurtosis and skewness. And measure of dispersion is range,
क्वार्टाइल मीडियन
quartiles,
स्टैंडर्ड
median, and standard deviation. Now this thing we already have discussed, right?
यस
Range is also discussed, which is maximum minus minimum. Quartiles is we have discussed. We divide our data into four equal parts. Here, measure of central tendency
मीडियन
is median. Now variance and standard deviation. See now, this is what you have to read. Why there is need of variance, why there is need of standard deviation, right? And We have square difference standard deviation. Okay, I'll share this thing. You give your time to read this, and after once you complete this, I'm going to discuss why there is need of standard deviation and variance. And if you want one more article on kurtosis and kurtosis and skewness, so you can read this as well. Right? Let me know if you are done with this. Just you read this thing only now, as of now. Standard deviation and uh, variance, dispersion of data. Read this. Yeah. So, see, in this thing, we are going to see what is the importance of range, why IQR is preferred across the range, why IQR is accept, why IQR accept data sorting in ascending order, impact of on outliers. So, what is range? Range is nothing but maximum minus minimum. What is maximum value? It is 37. Minimum is 19. So, range is 18. So range can influence by outliers. If there is one extreme value, that can change the value of range, right? 60 is your extreme value. Now range is 41. Now, so this is where quartile comes into the picture. Even though if you have outliers, your IQR value will not be influenced by the outliers, right? So this is a formula to find the IQR. We already have discussed this. Now we have variance. What is variance? It is a simple measure of dispersion. Variance measures how far each number in the dataset from the mean. To compute variance, first, what we have to do is we have to use this formula. Now see, what is happening is, suppose you calculate the variance, right? So suppose there is, what is variance meaning? Average square distance of data point with respect to mean, right? It is known as average square distance of each data point with respect to mean. So इसका वेरिएंस क्या रहेगा? इसका वेरिएंस कम रहेगा. What is variance for this? It is high, right? See, variance formula is average squared distance of each data point with respect to mean. Average square distance of each data point with respect to mean. So what we do is, suppose you have four data points. Suppose you have four data points. This is data point number one. This is data point number two. This is data point number three. Right? So from mean, this is center line is your mean, right? The center line is your mean. So distance of this data point is positive. ये जो distance है ये positive है, right? Suppose ये 1 है, this is 2 and this is 3, right? On the other hand, left hand side में अगर आप जाओगे, if you go to left hand side, the distance is negative. So let's say this is -3, this is -2, and this is -1. Now if you calculate sum of the distances, suppose you want to calculate sum. So -1, then 1, -2, 2, -3, 3. So can you see this? If you add this, it will be 0, right?
Yes.
So negative and positive can cancel each other. So that is the reason we have to take square of the distance. So that negative and positive will not cancel each other, right? If they cancel each other, there might be chance that distance could be 0. So you take square distance. Now square is 1, 4, 9, right? Here also 1, 4, and 9. Now, if you take sum, now if you take sum, the distance is 28 now. So for this, we take the average. It is average square distance of each data point with respect to mean. So distance is, so variance is 28, and this is known as standard deviation, which is square root of variance. Now, why do we take square root of variance? Why there is need of taking square root of variance?
Positive, negative values are present in the data.
Hmm?
There might be chance to the value or distance may get zero.
Yeah. So this 28 is not in the same unit as of your original distance. Can you see this? 28 is very high number, right? Distance is 149,941. So 28 is not the correct measure. It has to be in same unit, same range. So you take standard deviation, you take square root. By taking square root, it is 4.667, and it is in the same unit as of your original distance, right? So this is fine. This is how you should. This is how we take the square root. This is why we have to take the square root. Now, second point. See, if the distance is less, then standard deviation and your variance is less, right? If distance is high, the standard deviation and variance are high. So what do you think? Standard deviation का value high चाहिए या low चाहिए? What do you think?
Low
Yes, if it is low, then why?
the
Hmm?
the
See,
number is very close to the mean value.
right, right. See, why do we use this standard deviation variance? Because it helps to understand the deviation of the data points from the mean. Helps to understand the deviation of data point from the mean, right? So less the deviation, good is your model or good is your data. So less the standard deviation, less is the distance between data points and mean, and good good is your data, right? So this is your thumb rule. You have to remember this. Less the distance between data point and mean, less the standard deviation, and good is the mean or good is your data or mean, right? On the other hand, high is the distance. High would be the standard deviation, and bad would be your mean, right? Is it clear?
Yes, sir.
Yes, sir.
So this is your uh, variance and standard deviation. This is why it is important. Now let's watch.
Note: this StatQuest assumes you already know about histograms, statistical distributions, and, specifically, the normal distribution. If not, check out the quests. The links are in the description below. Also, this StatQuest assumes you already understand why we want to estimate population parameters. If not, check out the quest. In the StatQuest on population parameters, we counted the number of mRNA transcripts from gene X in 5 different liver cells. Alternatively, if mRNA transcripts in liver cells didn't mean anything to you, we counted the number of green apples in 5 different grocery stores, or green t-shirts in 5 different clothing stores, or whatever you want to measure in 5 different units. This green dot represented a liver cell that had 3 mRNA transcripts for gene X. And this green dot represented a liver cell that had 13 mRNA transcripts. 19, 24, and 29. Now, if we had a lot of time and money on our hands, we could count the number of mRNA transcripts for gene X in all 240 billion liver cells. Now we can draw a histogram of the measurements. If we wanted to fit a normal curve to this histogram like this, then we need to calculate the population mean and the population variance or population standard deviation. Calculating the population mean is easy. We take the average of all 240 billion measurements. Beep beep boo dee bee doo doo boo beep boo. Doo bee dee boo doo boo doo. And we get 20 for the population mean. And we center the normal curve on the population mean. Note: because we calculated the mean with all 240 billion measurements in the population, this is not an estimate of the population mean. It is the population mean. However, since we rarely, if ever, have enough time and money to measure every single thing in a population, we almost always estimate the population mean using a relatively small sample. In this example, we have the measurements from only 5 of the 240 billion cells. Estimating the population mean is super easy. We just calculate the average of the measurements we collected. And in this case, the estimated population mean is 17.6. Oh no, it's the dreaded terminology alert. Statisticians often use the symbol X bar to refer to the estimated mean, which is also called the sample mean. And they use the Greek symbol mu to refer to the population mean. The estimated mean, X bar, is different from the population mean, mu, but with more and more data, X bar should get closer and closer. Going back to the full set of population data, we will now determine how wide to make the curve by calculating, not estimating, the variance and standard deviation. In other words, we want to calculate how the data are spread around the population mean. This is the formula we use to calculate, not estimate, the population variance. Note, I'm making a big deal about calculating versus estimating variance because it makes a big difference that we'll talk about later. This part, x minus mu, means we subtract the population mean, mu, from each measurement, x. Boop 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 boop. Beep boop. The square tells us to square each term. And the Greek character sigma tells us to add up all the terms. Lastly, we want the average of the squared differences, so we divide by the number of measurements, n, which in this case is 240 billion. Thus, we're just calculating the average of the squared differences between the data and the population mean. Note, squaring each term ensures that each difference is positive. Otherwise, the measurements on the left side of the mean would give negative differences, which would cancel out the positive differences from the measurements on the right side of the mean. Note, if you are wondering why we don't take the absolute value of each term, great! We'll talk about that in the follow-up video that dives deep into these details. Anyway, now we just do the math. And we get 100 for the population variance. Bam! Okay, we calculated the population variance and we're all proud of ourselves. However, there is one thing that is annoying about it. Because each term is squared, the units for the result, 100, are mRNA transcripts squared. Note, if the data had been the number of apples in grocery stores, then the variance would be 100 apples squared. Either way, we can't plot the variance on the graph since the units on the x-axis are not squared. To solve this problem, we can take the square root of everything, and that gives us
That's why standard deviation comes into the picture, right?
the population standard deviation. So the population standard deviation is the square root of 100, the population variance, which is 10. And we can plot that on the graph. This shows the mean, 20, plus and minus the standard deviation, 10 mRNA transcripts. Bam! Note, before we move on, I want to emphasize the point that we almost never have the population data, so we almost never calculate the population mean and population variance and standard deviation. Instead, we estimate the population variance and population standard deviation from the relatively small number of measurements that we have. Remember, the population variance and standard deviation determines how much the curve spreads out. And that means the estimated variance and the estimated standard deviation should reflect how the data are spread around the population mean. However, when we do an experiment, we don't see the curve or the population mean. We only see the data. So we have to use the estimated mean, x bar, instead. This is the formula we use to estimate the population variance. Because we almost always work with a relatively small sample and not the entire population, this is the formula we will use most of the time. The differences between this formula and the one for the calculated population variance are subtle but important. First, since we don't know the population mean, mu, we use the sample mean, x bar. Second, we are dividing by n-1 instead of n. Dividing by n-1 compensates for the fact that we are calculating the differences from the sample mean instead of the population mean. Otherwise, we would consistently underestimate the variance around the population mean. This is because the differences between the data and the sample mean tend to be smaller than the differences between the data and the population mean. Thus, the differences around the population mean will result in a larger average. And the larger average is what we are trying to estimate. Note, if you're like me and want to know more details about why we need to compensate for calculating differences from the sample mean, check out the follow-up StatQuest. The link is in the description below. Now let's do the math. Just like before, we calculate the differences between the mean and the data. Then we square each term. Then we add up each term. But now we divide by n minus 1. And the estimated population variance is 101.8. Now we just take the square root of the estimated variance to get the estimated standard deviation. And we get 10.1. And we can draw the mean plus and minus the standard deviation on the graph. Double bam! The estimated population parameters correspond to this purple curve, with mean equals 17.6 and standard deviation equals 10.1. Which isn't too far off from the true distribution, with mean equals 20 and standard deviation equals 10. With more data, the estimated parameters would be more accurate and we would have more confidence in them. However, with just 5 measurements, we still did pretty well, and that saved us a ton of time and money. Hooray! In summary, if we have all of the data from a population, we can calculate the population mean. The population mean equals the sum of the measurements divided by the number of measurements, and that equals the average measurement, mu. When we don't have the population data, we can estimate the population mean with the same formula. The estimated population mean equals the sum of the measurements divided by the number of measurements, which equals the average measurement, x bar. When we have the population data, we can calculate the population variance and standard deviation. The population variance is the average of the squared differences between the data and the population mean, mu. In other words, we square these differences to prevent the ones on the left from canceling the ones on the right, and then take the average. And the population standard deviation is just the square root of the population variance. And since the standard deviation is in the original units that we measured, we can draw it on the graph. However, we almost never have the population data, so chances are you should not use these formulas. Instead, we almost always estimate the variance and standard deviation. When we estimate the population variance, we divide by n minus 1 to compensate for measuring distances from the sample mean instead of the population mean. And the estimated standard deviation is just the square root of the estimated population variance. And since the standard deviation is in the same units that we measured the data, we can draw it on the graph. And one last shameless plug for the follow-up StatQuest. If you want to know why dividing by n underestimates the variance, check out the quest. The link is in the description below.
Yeah. Is it clear or not? Somewhat.
Yeah, 50%.
Yes, Manju, Supriya.
Yes, sir. I got the concept.
All right. So now next is your kurtosis and standard deviation. Kurtosis and standard deviation. Sorry, skewness. Now see, what is kurtosis? There are 3 types of kurtosis. It describes the shape of the distribution. Describe the shape of the distribution. in terms of height or flatness. In terms of height or flatness. So first is your leptokurtic curve. Second is your platykurtic curve. And third is your mesokurtic. So remember these three types of kurtosis. Uh, let's discuss the three types of kurtosis now. Let's take this figure. Let's take this figure. See what is leptokurtic? जो सबसे हाई है, हाई इन द सेंस जिसका फ्लैटनेस और हाइट सबसे ज्यादा है. Then mesokurtic is middle, it's always in the middle. And platy मतलब flat, platykurtic distribution is flat, right? So किसका सबसे ज्यादा वेरिएंस और स्टैंडर्ड डेविएशन रहेगा? यस, सबसे ज्यादा वेरिएंस स्टैंडर्ड डेविएशन किसका रहेगा?
फ्लैट तो प्रोटीन का होगा.
Platykurtic is high, meso is middle,
सुपर कम.
and lepto is low, right? This is variance. This is types of kurtosis. Right? So platykurtic is high, mesokurtic is medium, leptokurtic is low. Right? So one more thing is, can we say like this, ki leptokurtic is having standard deviation less, so mean is good, right? So why do we use the kurtosis? Why do we use kurtosis? Because to check the quality of mean, to check the quality of mean, we have to use the kurtosis. So we have leptokurtic, we have mesokurtic. Standard deviation is moderate, and mean is moderate. Then we have platykurtic. For that, standard deviation is more, and mean is not good, right? So this is why we use the kurtosis. Second is kurtosis used to measure. It is measure, or it is used to measure, or we can put like this: it is measure to study whether standard deviation is good or not. It is used to measure whether standard deviation is good or not, right? So this is your kurtosis. And what is skewness? Skewness will tell you distribution. Is it off-centered, or it will tell you if the distribution is off centered or not. So there are two types of distribution as we have discussed, right? One is symmetric, that is normal distribution. This is your symmetric distribution. 50% to the left hand side, 50% to the right hand side. This is unsymmetric, and this is also unsymmetric, right? Now, see, this is your symmetrical distribution. Where mean is equal to median is equal to mode, and both are 0. This is your unsymmetrical. Where this is known as positive skewness. Why it is known as positive? Because here the distribution is not symmetrical, right? And wherever your tail, whenever your tail, this is your tail, whenever your tail is on the right hand side, it is known as positive skewness. ये जो tail है, इसको tail बोलते हैं. This is all on the positive, on the right hand side. So it is a positive skewness. Whenever your tail is on the left hand side, that becomes your negative skewness or left skewed. This is also known as left skewed data. Left skewed, and this is right skewed or positive skewed. Right? So for symmetrical, we have mean is equals to median is equals to mode. For unsymmetrical, we have mean greater than median greater than mode. Why mean is greater than? Because your graph becomes like this. So median is always will be in middle, mean is higher, mode is less. And on the left hand side, it will be reverse. Mode is higher, median is always middle, mean is less. Because most of the data points are on the left hand side, right? So if most of the data points are on the left hand side, mean will be shifted to the left hand side. If more number of data points are on the right hand side, mean will be shifted to right hand side. Yes or no, everyone?
Yes, sir.
So this is what you have. Is it clear now, this part? Yeah, so there are ranges for skewness and kurtosis. There are certain ranges for skewness and kurtosis. What are those ranges that we have? See now, first point is let's take the standard for kurtosis. Let's take the standard for kurtosis. So we have leptokurtic curve, we have mesokurtic curve, and we have platykurtic curve. For leptokurtic curve, kurtosis is greater than or equals to 1. For meso, it is closer to 0. And for platykurtic, it is less than or equals to -1. Right? -1 से कम रहेगा, so that is your which one? Platykurtic. If it is greater than or equals to 1, then that becomes your leptokurtic. And for kurtosis also, if it is less than or equals to -1, it is highly negatively skewed, right? If it is 0.9, 0.9 to 0.6, then it is moderately negatively skewed. If it is minus 0.5 to 0.5, it is approximately symmetric curve. It is approximately symmetric. Then it is approximately symmetric. Then if it is 0.6 to 0.9, it is moderately positively skewed. If it is greater than or equals to +1, it is highly positively skewed. Right? Now is this thing clear to you?
That moderate negative skewness is a minus 0.9, yeah, 0.9.
Minus. Minus रहेगा, right? It has to be minus. So these are the ranges. You have to remember this to understand the type of skewness or kurtosis. Now let us read about this. Instead of reading, let's watch the video. Kurtosis and skewness stats quest. Excuse me.
So I'm not getting any sound.
Yeah, I'm just having a look at this video if it is good or not. वैसे देख रहा है was that good or not? Do we have standard? वही है क्या? ठीक है।
Stats, how about you? When I'm awake, StatQuest. Hello, and welcome to StatQuest. StatQuest is brought to you by the friendly folks in the genetics department at the University of North Carolina at Chapel Hill. Today we're going to be talking about histograms, and they're going to be clearly explained. Imagine we went out and measured someone, and they were this tall. And then we measured someone else. And then we measured a whole bunch of people. We've measured so many people that the dots overlap. Some dots are completely hidden. We could try to make it easier to see the hidden measurements by stacking any that are exactly the same. But measurements that are the exact same are rare, and a lot of the hidden measurements are still hidden. So, instead of stacking measurements that are the exact same, we divide the range of values into bins and stack the measurements that fall in the same bin. This, my friends, is a histogram. Bam. The taller the stack within a bin, the more measurements we made that fall into that bin. Duh. We can use the histogram to predict the probability of getting future measurements. I would be willing to bet that the next measurement we make is somewhere in this range. Measurements out here are rarer and less likely to happen in the future. If you want to use a distribution to approximate your data or future measurements, histograms are a good way to justify your decision. By the way, if you don't know what a distribution is, there's a StatQuest for that. In this case, we might use a normal distribution to approximate the data and future measurements. If the data look like this, we might use an exponential distribution to approximate this data and future measurements. Note, figuring out how wide to make the bins is tricky. If the bins are too narrow, then they are not much help. In this case, the bins are so narrow that pretty much every measurement gets its own bin. This doesn't give us much more insight than what we had before, so it's not very useful. And if the bins are too wide, they are not much help. In this case, the bins are so wide that the measurements are split 50-50. All this tells us how many measurements are above the average and how many are below. This is more insight than before, but we can do better. Sometimes you have to try a bunch of different bin widths before you get a clear picture. In other words, don't rely on the default setting of whatever program you're using to draw the histogram. You've got to try a bunch of different settings before you're sure that you've got the best histogram you can draw. Hooray! We've made it to the end of another exciting StatQuest. If you like this StatQuest and want to see more like it, please subscribe. It's really easy. And if you have any suggestions for future StatQuests, just let me know in the comments below. Until next time, quest on. Stat quest, stat quest, stat quest, stat quest, stat quest. Hello, and welcome to StatQuest. StatQuest is brought to you by the friendly folks in the genetics department. Be talking crazy dance party, and you overhear someone talking about. Imagine you're at a wild and crazy dance party, and you overhear.
So specifically, he has not talked about these Cartesian skewness, no? Okay, let's go for this simply learn. Let's see what they're talking about.
measurements are distributed
about the different types of data and their associated properties. So, in this session, we'll discuss how to calculate the distortion in the normal curve using skewness and kurtosis. So, let's get started. We will start this tutorial by understanding symmetrical distribution. Then we'll move on to discuss skewed distribution and Pearson's coefficient of skewness. Finally, we will discuss kurtosis. So, let's get started. Symmetrical distribution. A distribution is said to be a symmetrical distribution when it is equally distributed on both the sides of the mean value. The distribution shape can either be a bell-shaped or U-shaped. In symmetrical distribution, the values of mean, median, and mode are all equal, as you can see in the graph. Skewed distribution. Skewness is used to measure the level of asymmetry in our graph. It is a measure of asymmetry that occurs when our data deviates from the norm. Sometimes the normal distribution tends to be tilt more on one side. This is because the probability of data being more or less than the mean is higher and hence makes the distribution asymmetrical. This also means that the data is not equally distributed. The skewness can be of two types: positively skewed and negatively skewed. Let's discuss them separately. Negatively skewed. In a negatively skewed distribution, the data points are more concentrated towards the right-hand side of the distribution, as you can see in the graph. This makes the mean, median, and mode bend towards the right. Hence, these values are always negative. In this distribution, mode is greater than median and median is greater than mean. Now let's move on to positively skewed distribution. In a distribution that is positively skewed, the values are more concentrated towards the right side, and the left tail is spread out, as you can see in the graph. Hence, the statistical results are bent towards the left-hand side. Therefore, the mean, median, and mode are always positive. In this distribution, mean is greater than median and median is greater than mode. The measure of skewness always helps us to know to what degree and in which direction, positive or negative, the frequency distribution has a departure from symmetry. Positive or negative skewness can be detected graphically depending on whether the right tail or the left tail is longer, but we don't get the idea of the magnitude. In a negatively skewed symmetry, the values are always negative. This is the symmetrical distribution, and in a positively skewed, the values are always positive. Now let's discuss Pearson's coefficient of skewness. The median is always the middle value, and the mean and the mode are the extremes. So we can derive the formula to capture the horizontal distance between the mean and the mode using the Pearson's first coefficient. So the formula to calculate the Pearson's coefficient is mean minus mode divided by the standard deviation. The division by the standard deviation will help you to scale down the difference between the mode and the mean. This will scale down their values in the range of -3 to +3. In case where the mode is indeterminate, we can calculate the Pearson's coefficient by mean minus 3 median minus 2 mean divided by the standard deviation. If the value of coefficient is between -0.5 and 0.5, the distribution of the value is always symmetrical. If the value of coefficient is 0, then the distribution is symmetrical. If the value of coefficient is positive, then the distribution is positively skewed, and if the coefficient is negative, then the distribution will be negatively skewed. Now that we have discussed this symmetrical and skewed distribution, let's move on to understand what is kurtosis. Kurtosis is used to find the presence of outliers in our data. It gives us the total degree of outliers present. The data can be heavily tailed, and the peak can be flatter, almost like punching the distribution or squishing it. While skewness signifies the extent of the symmetry, kurtosis measures the degree of peakness of a frequency distribution. When the peak of the curve becomes relatively high, then the curve is called leptokurtic. And when the curve is flat, it is called platokurtic. When the curve is similar to a normal curve, it is called mesokurtic. The expected value of kurtosis is 3. This is observed in a symmetrical distribution. A kurtosis greater than 3 will indicate positive kurtosis. Further, a kurtosis less than 3 will mean a negative kurtosis. The range of value for a negative kurtosis is from -2 to infinity. The greater the value of kurtosis, the higher is the peak, as you can see from the graph. With this, We come to an end to this tutorial. Let's conclude what we have learned. You can say that skewness and kurtosis are used to describe the spread of height of a normal distribution. Skewness is used to denote the horizontal pull of the data. It tells you how spread out the data is, and the kurtosis is used to find the vertical pull or the peak's height. Thank you all for watching this session. We hope you enjoyed it. If you have any questions, feel free to put them in the comment section of this video. Thank you again and happy learning.
So it gives you the distribution, right? It gives you if your distribution is off-centered, skewness will give you your distribution is off-centered, and kurtosis will tell you the shape of the distribution in terms of height and flatness, right? So this is what we have. I'll just quickly share this on your drive. And if you have any questions, you can ask. Yeah. Do you guys have any questions?
No, sir.
Hello, Vipul.
Yeah.
This is a statistics class is going on Python.
Python is completed. We have started the new module, statistics.
Okay, because last 2 to 3 days I did not attend the class. Today is second day.
Hmm?
Today is second day. Statistics started. No, today is second day.
Today is
Is it second day? How many days got our statistics class is going on?
I think it's second day only. Second.
Okay. Okay.
Sir, when the Excel classes will start?
Hmm?
When the Excel classes will start, sir? Excel.
Excel. Okay. Let's see. After statistics, we can start. See, what I'm doing is we are starting the class at 8:45 a.m. 8:45. So this time would be good, right, for you?
Yes, 8:45 is fine.
This will work, no?
Yeah, yes, sir, it is good.
8:45 to 9:45.
Yes, sir.
All right. Yeah, I'm just uploading this. Okay. Anybody have any doubts? See, this is your link. I'm sharing this on the chat as well as on your classroom. Yeah. All right. Thank you. Happy learning.
Thank you, sir.
Thank you.